Okay. Check 1, 2.
Yeah.
Is this thing on? Is the red light blinking?
Seriously, we're in the library, the quiet section. If we get kicked out, I lose this outlet, and my laptop is at like 11%.
Right, right. Sorry. It's just
What?
the exam is tomorrow, and the caffeine is definitely kicking in. Okay. Welcome to the psychology undergrad.
A special, high-stakes study session for anyone who's feeling a little overwhelmed right now.
I think overwhelmed is the understatement of the semester.
Right.
If you're listening, you probably have the same list we do. The professors must know terms for the research methods final.
It's less of a list and more of a scroll. I had to tape 2 pages together.
It is genuinely terrifying. And we're not just going to read definitions. I mean, if I read the textbook definition of construct validity one more time, my brain will actually leak out of my ear.
No definitions. That's not how you study. We're going to translate. We're turning this textbook jargon into, real life.
We're going to use bad analogies, pop culture, whatever it takes to make this stuff stick.
And maybe, touch on the bigger picture. Psychology is the study of the soul, or mind. So these rules, these methods, they're all about how we search for truth. There are weird links to morality and stuff in here, too.
I love it. Okay, get your highlighters ready. Let's do this. First up, the professor has a whole section on measurement and reliability. I'm calling it the yardstick of truth.
That's a good name for it, because you can't study anything until you can measure it. In physics, that's easy. You have a ruler, a scale, a thermometer.
But we're trying to measure things you can't see. Like, how do you measure happiness or anxiety?
Exactly. You can't put love in a beaker. So we have to start with the absolute basic term, measurement. And all it is, really, is assigning numbers to variables.
It sounds so simple, but it's everything. It's like rating a movie on a scale of 1 to 10.
Totally. Or when you go on a date and your friend asks how it was, you say, a 6 out of 10.
You just took this incredibly complex social interaction, the awkward silences, the good jokes, whether they chewed with their mouth open, and you boiled it all down to one number, a 6.
And that's measurement. But here's the first problem, and the first big term on our list. Is your 6 the same as my 6?
Probably not. My 6 could be your 8.
Right. And if our numbers don't mean the same thing, then we have a problem. Which brings us to reliability.
Okay, reliability. The textbook says it's about consistency.
That's the key word, consistency. Stability. Does the measure give you the same answer again and again? The classic analogy is the bathroom scale.
Right, so I step on the scale, it says 160 pounds. I step off, I step back on, it says 160 pounds again. Do it 5 more times, always 160. That scale is super consistent.
It is highly reliable. It gives you the same number every time, but, and this is the trick question they love for exams, is it accurate?
Not necessarily. It could be broken. It could be consistently 10 pounds heavy.
Yeah.
So I actually weigh a 150, but it reliably tells me I'm 160.
Bingo. And that is the absolute core distinction. That scale is reliable, but it is not valid. It's consistently wrong. You can have reliability without validity.
But you can't have it the other way around.
You can't. If the scale said 150, then 200, then 110. It's totally unreliable. It's useless. You can't even begin to ask if it's accurate because it's just spitting out random numbers.
Okay, that makes sense. Reliability is the first step.
Yeah.
But how do we apply that to psych stuff, like a personality test?
We use something called test-retest reliability. It's exactly what it sounds like. I give you an introversion-extroversion test today. Then I give you the same test a month from now.
My score should be pretty similar.
It should be. Your personality is supposed to be a stable trait. You shouldn't be a raging extrovert on Tuesday and a shy introvert on Friday. If the test says you are, it has low test-retest reliability. It's a bad test.
There was that study in the notes, the one about faces, the felt study.
Yes. Perfect example. The facial expression labeling task. They showed people pictures of faces making different emotions, anger, fear, happiness, and had them label the emotion.
Sounds simple enough.
It is, but they tested people, including twins, multiple times over a few weeks, and they found really high correlations, like 0.80, between the first and second tests.
0.80 is really good on a scale of 0 to 1.
Very good. It means your ability to recognize fear or anger on someone's face is a stable skill. It doesn't change much day to day. So the felt is a reliable measure.
Okay, so that's reliability over time. What about reliability within a single test?
Yeah.
That's internal consistency, right? This one always trips me up a bit.
Yeah, this one's a little more abstract. Think of it like this. Are all of the questions on your test pulling in the same direction? Imagine I'm making a self-esteem quiz.
Okay.
Question 1 is, I generally feel good about myself. Question 2 is, I am confident in my skills. Question 3 is, I enjoy the taste of asparagus.
One of those things is not like the others.
Exactly. Your feelings about asparagus have nothing to do with your self-esteem. Someone with high self-esteem might love it or hate it. That question doesn't correlate with the others. It's noise.
So it lowers the internal consistency of the test. It's not a unified measure anymore.
Precisely. And the stat we use to measure this, and you absolutely have to know this name, is Cronbach's alpha.
Cronbach's alpha. Sounds like a villain from a sci-fi movie.
It does, but what it does is kind of genius. It's like a computer takes all the questions on your test, splits them in half randomly, and compares the scores. Then it does it again with a different random split. And again, it does this for every possible way of splitting the test in half.
Wow, okay.
And if, on average, the two halves always give you a similar score, it means the questions are all hanging together. You get a high alpha score, high internal consistency.
That makes so much more sense now. It's a teamwork score for the questions.
Okay.
Third type of reliability. Inter-rater reliability.
Or inter-observer reliability. This is huge for observational studies. Imagine we're on a playground, and our job is to count aggressive acts between kids.
Okay.
I see a kid shove another kid, and I write down one act of aggression. But you see the same thing, and you think it was just playing. You write down 0.
We have a problem. Our data is garbage because we can't agree on what we're even looking for.
We have low inter-rater reliability. We need to have a very clear definition of aggression so that when we both see something, we both code it the same way. The statistic for this is Cohen's kappa.
Another Greek-sounding name.
It is, but the idea behind it is ancient. It's actually a core principle of justice in many legal and even religious systems. The Old Testament, for instance, requires 2 or more witnesses to establish a fact in court.
Oh, interesting. Why?
Because one person's view is subjective. It's just their opinion. But if 2 independent people see the same thing and agree on what it was, you're getting closer to something objective, something you can call truth.
2 witnesses. That's a great way to remember it. Okay, so we've established our yardstick is consistent, it's reliable. But now the bigger question, is it measuring the right thing? This is validity.
Yes, validity of a measurement. This is all about accuracy. Back to our scale, that's 10 pounds off. It was reliable but invalid. Validity asks, does this test actually measure what it claims to measure?
And the most important type, the umbrella term for all of this, is construct validity.
This is the big one. This is the concept that holds everything together. A construct is the abstract idea we care about. Intelligence, depression, creativity.
The thing you can't see.
Right. And our test or survey is the operational definition. It's how we try to make that invisible thing visible and measurable. Construct validity is the question. Does our definition actually capture the essence of the real construct?
So an example. If I say my construct is athletic ability and my operational definition is how many hot dogs you can eat in a minute.
Your measure has a terrible construct validity. You're not measuring athleticism. You're measuring competitive eating ability. It's the wrong target.
A more realistic one would be using a final exam score to measure how much you learned in a class.
Perfect example. We assume it does, but does it really? Or does that score just measure your ability to memorize facts? Or how good you are at taking multiple choice tests? Or how low your test anxiety is?
It's probably a mix of all those things.
Exactly. So its construct validity as a pure measure of learning is probably not as high as we'd like to think.
Okay, under the big umbrella of construct validity, we have some smaller types. First, face validity.
The easiest one. Does it just look like it's measuring the right thing on the surface? It's the smell test.
Like if I give you a survey that I claim measures depression, and the questions are, do you feel sad? And do you have low energy? Oh, that has good face validity.
Yes. But if the questions were, what's your favorite type of bird? And how many siblings do you have? It would fail the smell test immediately. It's not super scientific, but it's important. If a test looks dumb, people won't take it seriously.
Got it. Next up, criterion validity.
This one is about prediction. Does your measure score actually predict some real-world outcome? The outcome is the criterion.
The SAT is the classic example here.
It is. The College Board claims the SAT measures your readiness for college. The construct is college readiness. The criterion, the real-world outcome, is your actual GPA in college.
So to test its criterion validity, you see if high SAT scores predict high college GPAs.
Exactly. If people with perfect SAT scores are flunking out of freshman year, then the SAT has very poor predictive validity. It's not doing the job it claims it can do.
Okay, that makes sense. And the last one in this section is content validity.
This is about coverage. Does your test cover the entire breadth of the concept? Imagine our research methods final tomorrow. We studied measurement, sampling, design, ethics, a ton of stuff.
Right.
But when you open the exam, every single question is about Cohen's kappa. Just that one concept.
I would be so mad.
Of course, the test would lack content validity. It's supposed to measure your knowledge of the whole course, not just one tiny part of it. It has to be a representative sample of the content.
Okay. Wow. That was a lot. But I think I've got a handle on the yardstick of truth now.
Good, because now we have to talk about the person holding the yardstick
Right.
and the person being measured. Section 2, the human element.
This is where it gets messy, because people aren't chemicals in a test tube.
Nope. People have thoughts, feelings, and they know when they're being watched, which leads directly to participant reactivity.
The act of observing something changes the thing being observed.
It's the Heisenberg principle of psychology. The moment a participant knows they're in a study, they might act differently. They might try to be a good participant and help you out. That's called participant expectancy.
Or they might get nervous and try to hide their flaws.
Right, that's evaluation apprehension. They're worried you're judging them, so they put on their best face. It's also sometimes called social desirability, which we'll get to, again, with service.
It's that God is watching effect again, right?
Yeah.
We act more moral or proper when we think someone is observing us.
Totally. It messes up the data because you're not seeing how people naturally behave, you're seeing their performance.
And it's not just the participants who are the problem. It can be us, the researchers. Experimenter bias.
This is when the researcher's own expectations unintentionally influence the results. It's usually not conscious cheating, it's subtle.
The textbook had that example of the broken down car study.
Yeah, that's a great illustration. A researcher has a hypothesis that men are more likely to help a stranded motorist than women, so they stage a car with a flat tire.
And they find that, surprise, men stop to help more often.
Right. But was it because men are naturally more helpful? Or was it experimenter bias? Maybe when a car with a man driving approached, the researcher looked more distressed. Maybe they waved their arms more.
And when a woman drove by, maybe they just sort of stood there looking less desperate.
Exactly. The researcher's own bias could have created the very effect they were looking for. The solution, by the way, is a double-blind study where neither the participant nor the researcher interacting with them knows what the hypothesis is.
Okay, 2 more measurement issues here. First, sensitivity of measurement.
This is about having the right tool for the job. Is your measure sensitive enough to detect the small changes you're looking for?
Like trying to weigh a feather on a bathroom scale?
Perfect analogy. The scale isn't sensitive enough. It will just read 0. In psychology, imagine you're studying an eating disorder intervention. If you measure their progress by weighing them on a scale that only shows pounds, you might not see any change for weeks.
But if you used a more sensitive scale that measures grams or ounces, you might see small, steady progress.
Exactly. You need a sensitive instrument.
And the flip side of that is the range effect of measurement.
This is when your measure is basically broken because the task is either way too easy or way too hard.
So a ceiling effect.
That's when the task is too easy and everyone gets a perfect score. Imagine giving a 2+2 math test to a class of college students. Everyone gets 100%.
The scores are all bunched up at the top on the ceiling. You can't tell who's a math genius and who's just average because the test wasn't hard enough to show any variation.
Right. And the opposite is a floor effect. The task is too hard and everyone gets a 0, like giving a graduate-level physics exam to 3rd graders.
Everyone fails. Their scores are all on the floor. You can't distinguish between the kids because the test was impossible for all of them.
Both effects are bad because they restrict the range of your data and hide the true differences between people.
Okay. I think we've navigated the minefield of measurement. Now, section 3. Who are we actually studying? This is all about sampling.
Right. So you have your perfect, reliable, valid measure. Now you need people to use it on. First, you have to define your target population.
This is the entire group you're interested in, like all college students in the United States, or all people with anxiety disorders.
It's usually huge and impossible to actually reach. So you have to narrow it down to the accessible population, which is also called the sampling frame.
So that would be the people you can realistically get access to. For us, that's all the students in the Psych 101 subject pool at our university.
Exactly. And from that accessible population, you draw your sample. That's the small group of people who actually participate in your study.
And the dream, the absolute goal, is to get a representative sample.
The holy grail of sampling. A sample that is a perfect miniature version of the target population. It has the same percentage of Men and women, the same age distribution, the same racial demographics, everything.
Why is that so important?
Because if your sample is representative, you can generalize your findings. You can say that what you found in your little group of 100 students is probably true for the entire population of millions.
If it's not representative, you can't generalize. Okay, so how do we get this magical sample? The best way is probability sampling, starting with simple random sampling.
This is the purest form. Every single person in the population has an equal chance of being selected. It's like putting everyone's name into a giant hat and drawing them out one by one.
But that's probably really hard to do in real life.
It's almost impossible for large populations, so there are other methods, like systematic sampling.
That's where you take a list of everyone and you pick, like, every 10th person on the list.
Right. You pick a random starting point and then you select every nth person. It's easier than drawing from a hat, and as long as the list isn't ordered in some weird way, it works almost as well as random sampling.
Okay, what about stratified random sampling? The name sounds complicated.
It's actually a really clever way to guarantee representation. Strata just means layers or subgroups. Let's say you know your population is 60% women and 40% men.
Okay.
If you do a simple random sample, by chance you might end up with 70% men. Your sample wouldn't be representative. So with stratified sampling, you first divide your population into two strata, men and women.
And then you sample randomly from within each group. So you'd randomly select 60 women and 40 men to make sure your sample matches the population percentages.
You got it. It guarantees your sample structure mirrors the population structure.
And the last probability one is cluster sampling.
This is what you use when your population is spread out all over the place, like all high school students in California. You can't get a list of all of them.
So what do?
You randomly sample clusters, which are pre-existing groups. So you'd randomly select 50 high schools from across the state. Those schools are your clusters. Then you go to those 50 schools and you test every single student in them.
So you're sampling the groups, not the individuals.
Exactly. It's much more practical. Now, that's the ideal world. In reality, most psychology studies use non-probability sampling.
Because it's easier and cheaper.
Way easier, which leads to sampling bias. This happens when your sampling method favors some people over others. The classic example is doing a phone poll, but only calling landlines.
You're only going to reach older people. You're completely missing young people who only have cell phones.
Right. Your sample is biased towards the elderly, and your results will not represent the whole population.
And then there's response bias. This seems similar.
It's a different problem. This happens after you've selected your sample. Let's say you send out a survey to a perfect random sample of 1,000 people, but only 100 people send it back.
That's a low response rate.
It's a terrible response rate. And the problem is, those 100 people who chose to respond are probably different from the 900 who didn't. Maybe they have stronger opinions or more free time. They are a self-selected group. That's response bias or non-response error.
Okay, my head is spinning with all this sampling stuff.
Yeah.
I feel like I need to consolidate this information.
Cognitive overload is a real thing. Your short-term memory can only hold so much.
I know what I need. I need to sleep, like a deep, restorative, memory-consolidating sleep after this exam.
That's actually the most important part of studying. If you don't sleep, the information doesn't move from your hippocampus to your cortex.
But when I do finally get to sleep, I want it to be amazing. Which is why we need to talk for a second about our sponsor, Cozy Earth.
Ah, the famous bamboo sheets.
You know it. Their bamboo sheet set is, I'm not kidding, the softest thing I've ever felt. It is like sleeping in a cool, soft cloud.
And they're temperature regulating, which is actually super relevant. A drop in core body temperature is a physiological signal that helps initiate sleep, especially REM sleep. If your sheets make you hot, you're disrupting that process.
So better sheets equals better sleep, which equals better memory consolidation for all these terms. It's basically a study tool.
A very comfortable study tool.
Look, I know we're undergrads, we don't have a lot of money, and nice sheets can be expensive. But this is an investment in your GPA. Plus, we got you a deal. If you use the promo code PSYC101,
that's PSYC101.
you get 21% off your order. So go to cozyyours.com/discount, PSYC101. Seriously, get the sheets. Your brain will thank you. Okay, ad break over. Back into the fray.
Let's do it. Section 4, the truth of the design. This is where we talk about the two big types of validity for a whole study.
Internal validity and external validity.
The great trade-off. Internal validity is all about control. It's the degree to which you can be sure that your independent variable X was the real cause of the change in your dependent variable, Y.
So did my new study technique really cause my grade to go up, or was it something else?
Exactly. And external validity is about generalizability. Does what you found in your highly controlled lab experiment actually apply to the messy real world?
And they're often in conflict. The more you control things in a lab to get high internal validity.
The less it looks like the real world, so the lower your external validity becomes. It's a constant balancing act.
Okay, let's talk about the bad guys. The threats to internal validity. These are the something else's that could have caused the effect. First up, history.
And this doesn't mean things that happened in the past. It means a specific external event that happens during your study that affects your results.
The example in the notes was doing an anxiety study around 9/11.
Right. Imagine you're in New York City. You measure people's anxiety on September 10th. You start your amazing new anxiety reduction therapy. Then 9/11 happens. You measure their anxiety again on September 12th.
It's going to be through the roof.
Exactly. It would look like your therapy made everyone's anxiety worse. But it wasn't your therapy. It was history. That confounding event destroyed your study's internal validity.
Okay, next threat. Maturation.
This is just about people changing naturally over time. They get older, they get wiser, they get tired, they get hungry. If you do a 9-month study on a new reading program for first graders, they're going to be better readers at the end.
But is it your program, or is it just that they had 9 more months of brain development?
That's the question. Maturation is a huge confound in developmental research.
Third one, testing.
This is a practice effect. People get better at a test just from taking it before. If I give you an IQ test and then give you the exact same test a week later, your score will probably go up. Not because you got smarter, but because you're familiar with the questions.
So the first test acts as a kind of intervention itself.
It does. It contaminates the results of the second test.
Okay, instrumentation.
This is when the measuring tool itself changes over the course of the study. This is a big problem when the instrument is a human observer.
So like a researcher grading essays gets tired and starts grading more leniently toward the end of the stack.
Precisely. The grading standard, the instrument has changed. It's not consistent.
This next one always sounds so weird. Regression toward the mean.
It sounds mystical, but it's just a statistical fact. It means that extreme scores on any measure tend to move closer to the average when you measure them a second time.
The famous Sports Illustrated curse.
Perfect example. An athlete has an unbelievable record-breaking season, an extreme performance. They get on the cover of Sports Illustrated. The next season, they're just good, not godlike.
So people say the magazine cursed them.
But it's not a curse. It's regression to the mean. That amazing season was an outlier. Statistically, it's just very likely their next performance will be closer to their personal average. The extreme score regressed back toward the middle.
That makes a lot of sense.
Yeah.
The rubber band analogy in the outline was helpful too. You can stretch it way out, but it wants to snap back to the average.
Exactly.
And the last big threat, differential attrition.
Attrition is just a fancy word for participants dropping out of a study. Differential means the dropout rate is different across your groups.
So imagine you're testing a difficult new workout regimen against a control group that just watches TV.
People in the workout group are way more likely to drop out because it's hard. The people who are less motivated will quit.
So at the end of the study, the only people left in the workout group are the super motivated fitness fanatics, and they look great.
Right. But you can't conclude the workout caused the results. Maybe you just filtered out all the unmotivated people. The groups are no longer equivalent because of who dropped out.
Okay, so those are all the villains. What are our superhero weapons against them?
We have two main ones, control and randomization.
Control means keeping everything except your independent variable exactly the same for all groups.
And randomization, or random assignment, means you randomly decide who goes into which group. This should, in theory, spread all the weird individual differences, motivation, intelligence, anxiety evenly across the groups.
So that no single group has an unfair advantage. It neutralizes the confounding variable.
That's the goal. The confound is the extra variable you didn't account for that's secretly causing the effect.
Like the classic example, ice cream sales are correlated with murder rates.
Right. Does eating ice cream make you a killer? No. The confounding variable is the weather. When it's hot, people buy more ice cream, and they also get more irritable and spend more time outside, leading to more crime. The heat causes both.
Okay, section 5. We're moving out of the lab. Non-experimental research.
Sometimes you can't or shouldn't do an experiment. Sometimes you just have to observe the world as it is, which leads to naturalistic observation.
This is Jane Goodall watching the chimpanzees.
Yeah.
You go to their natural environment and you watch, you take notes, but you don't interfere.
Right. But you have to be sneaky about it. If the chimps or people know you're there, they'll act differently. Remember participant reactivity.
So you need unobtrusive observation or non-reactive observation.
Exactly. You might hide in a blind, or use a hidden camera, or just sit in a coffee shop for so long that people stop noticing you're there. And again, you need at least 2 observers to make sure you have good inter-observer reliability.
Okay, what about using data that's already out there? That's archival research.
Yep. You're digging through existing records, census data, hospital records, crime statistics, newspaper articles. It's great because the data is already collected. It's cheap and easy.
What's the downside?
You have no control over how it was collected. It might be messy or incomplete. You're at the mercy of whoever created the archive.
Similar to that is content analysis.
This is where you systematically analyze the content of communications. You could analyze children's books to count how female and male characters are portrayed, or analyze political speeches to look for certain themes.
And then there's meta-analysis.
The study of studies. Let's say 50 different studies have been done on a new antidepressant. Some found it works great, some found it does nothing. A meta-analysis mathematically combines the results of all 50 studies to find the overall average effect.
So it's a way of getting a clearer signal from a lot of noisy data.
A very powerful way, yes. Okay, let's talk about surveys. 2 types of questions. Open-ended question versus closed-ended or restricted question.
Open-ended is like an essay question. How do you feel about the current political climate? You can write whatever you want.
You get rich, detailed data, but it's a nightmare to score and analyze. A closed-ended question gives you options. On a scale of 1 to 5, how satisfied are you?
Much easier to analyze, but you lose all the nuance. And that scale, the 1 to 5, strongly agree to strongly disagree, that's a Likert scale.
The most famous scale in psychology, you'll see it everywhere.
Now, a big problem with surveys is social desirability.
People lie to make themselves look good. It's that morality thing again. We want to present ourselves as virtuous. If you ask how often do you donate to charity, people are going to inflate their answers.
And we also have to worry about the response rate or return rate.
Yes. If you email a survey to 1,000 people and only 50 respond, you have a 5% response rate, which is terrible. You can't trust the results because those 50 people are probably not representative of the 950 who ignored you.
And then there's the problem of the response set.
This is just pure laziness from the participant. It's when they get tired of thinking and just start answering the same way for every question. They'll just circle agree, 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 agree all the way down the page just to be done with it.
It's garbage data. Okay, last thing in this section. Correlational research.
The big mantra. Say it with me.
Correlation does not equal causation.
But we still do it all the time. Why? Because sometimes it's the only ethical option. You can't randomly assign people to be smokers to see if it causes cancer. You have to look at existing smokers and see if there's a correlation with cancer rates.
So it could suggest a relationship, but it can't prove it.
Exactly.
Okay, section 6. We're in a weird middle ground now with quasi-experiments.
Quasi means almost or resembling. So these look a lot like true experiments, but they are missing the key ingredient, random assignment.
And you use them when you can't randomly assign people to groups, like the smoker example. Or you can't assign someone to be male or female.
Right. You have to use pre-existing non-equivalent groups. There are a few different designs here. Some are very weak. The weakest is the one group post-test only design.
This sounds terrible. You just give a group a treatment and then you measure them.
Yep. It's basically useless. You have no idea if they changed because you have no baseline to compare it to.
A little better is the one group pre-test, post-test design.
So you measure them, you give the treatment, and you measure them again. Now you can see if there was a change, but you don't know what caused it.
Right. Could have been history or maturation or testing effects.
Exactly. So to get better, you need a control group. This leads to the non-equivalent control group post-test only design.
So you have 2 groups that weren't randomly assigned, like 2 different classrooms, and you give the treatment to one but not the other, then measure both at the end.
Better, but the groups might have been different from the very start. Maybe one class just had smarter kids.
So the best quasi-experimental design is the non-equivalent control group pre-test, post-test design.
Yes. You measure both groups at the start and at the end. This lets you see if they were different to begin with, and you can see if the treatment group changed more than the control group. It's the strongest of the quasi-designs.
Okay, what about interrupted time series designs?
These are really cool for evaluating real-world events, like a new law being passed. You collect data at many points in time before the event, and at many points in time after the event.
So you could look at traffic fatalities for 5 years before a seatbelt law was passed and for 5 years after.
And if you see a sharp, sudden drop in the graph right at the point the law was implemented, that's pretty strong evidence the law worked.
Okay, now let's talk about time. Developmental designs. Cross-sectional design.
This is where you compare different age groups all at the same time. You get a group of 20-year-olds, 40-year-olds, and 60-year-olds today and test their memory. It's fast. You get your data in one day.
But the big problem is cohort effects.
Huge problem. A cohort is a group of people born around the same time who share similar life experiences. The 60-year-olds didn't just grow older, they grew up without the internet. The 20-year-olds grew up with it. So are the differences in memory due to age or due to their different life experiences? You can't tell them apart.
So to fix that, you do a longitudinal design.
This is the ultimate design for studying development. You take one group of people, one cohort, and you follow them for their entire lives. You test them when they're 20, 40, 60, 80.
It gets rid of cohort effects.
But it takes 60 years, it's incredibly expensive, and people die or move away, which is attrition. It's very difficult to pull off.
So there's a hybrid. The cohort sequential design.
The best of both worlds. You take several different cohorts, say a group of 20-year-olds and a group of 40-year-olds, and you follow both of them for a shorter period, like 10 years. It lets you check for both age effects and cohort effects.
Okay, section 7. We're zooming in from huge populations to just one person, single case, or a single subject, research design.
Sometimes called N of 1 designs. This is really common in clinical psychology or special education, where you're trying to see if a treatment works for one specific individual.
The first thing you need is a baseline. That's phase A.
Right. You have to observe and measure the person's behavior before you start any treatment. You need to know what their normal is.
And then you introduce the treatment phase. That's phase B.
You start the therapy or the medication or the behavioral plan, and you keep measuring.
Which brings us to the reversal design, or ABA design.
This is the classic single subject design. You get a baseline, A, then you introduce the treatment, B, and then this is the key part. You take the treatment away and go back to baseline A.
Why would you take it away?
To prove it was the treatment that caused the change. If the behavior gets better during B and then gets worse again when you go back to A, you have very strong evidence that your treatment was effective.
But that seems unethical sometimes.
It can be. This is a huge ethical dilemma. If your treatment B is stopping a child from engaging in self-harming behavior, is it morally okay to remove that treatment? A, just to prove a scientific point.
No, of course not. You're making them suffer for the sake of your data.
I agree. So for those situations, we have better designs, like the ABA design.
So you go baseline, treatment, baseline. But then you add the treatment back in at the end.
Yes, you end the study with the person benefiting from the effective treatment. Much more ethical.
Or you can use a multiple baseline design.
This avoids the reversal altogether. Let's say you want to teach a child 3 new social skills. You get a baseline for all 3. Then you start the treatment for skill 1, while skills 2 and 3 are still in baseline. A few weeks later, you start the treatment for skill 2. Then later for skill 3.
So you're staggering the start time of the treatment across different behaviors.
Yes. And if each behavior only improves right after you start treating it, that's strong evidence the treatment is working and you never had to take anything away.
And the last one here is the changing criterion design.
This is for when you're trying to gradually shape a behavior. Let's say you want a student to increase the number of minutes they spend reading each day. First, you set the criterion for a reward at 5 minutes. Once they're consistently doing that, you change the criterion to 10 minutes. Then 15.
You keep raising the bar.
And if their behavior closely follows the changes in the criterion, you know your reward system is working.
And for all these single case designs, you're not usually running complex stats. You're looking at the graphs. You're looking for the stability of measure.
Meaning the baseline isn't all over the place, and the magnitude of change, meaning there's a big, obvious jump when the treatment starts.
Okay, we're here. The final section, the big one. Section 8, the experiment.
The true experiment, the gold standard, the only research design that can definitively prove a cause and effect relationship.
Let's get the vocabulary straight. A factor is just another name for the independent variable.
Yep. If we're studying the effect of caffeine on memory, caffeine is our factor.
And a level is one of the specific values of that factor.
So if we have a no caffeine group, a low caffeine group, and a high caffeine group, our factor has 3 levels. Each level is a condition or a treatment.
Now, how we assign people to those conditions is a huge deal. First option, A between subjects design?
This is when you have different people in each condition. Group A gets no caffeine. A totally separate Group B gets low caffeine. A third Group C gets high caffeine.
What's the main pro of that?
It's clean. Each person only experiences one thing, so there's no chance of one condition contaminating another. But the con is that you need a lot more people, and you have to worry about the groups being different to begin with because of individual differences.
Which is why random assignment is absolutely critical in a between subjects design.
It's the only way to make it work.
The other option is a within subjects design, or a repeated measures design.
This is where the same people experience all of the conditions. So you come into the lab, you drink no caffeine and take a memory test. Then you come back the next day, drink low caffeine and take another memory test. Then the third day, high caffeine.
The big advantage is you need fewer people, and you get rid of the individual differences problem because you're comparing people to themselves.
It's a much more powerful design, but it has its own huge problem, order effects.
Right. Maybe you did better on the third day, not because of the high caffeine, but just because you'd practiced the memory test twice already.
That's a practice effect. Or maybe you did worse because you were bored and tired of coming to the lab. That's a fatigue effect. There's also the carryover effect.
Where the effects of one condition haven't worn off before you start the next one. Like the caffeine from day 2 is still in your system on day 3.
Exactly. So what's the solution to order effects?
Counterbalancing.
Yes. You vary the order of the conditions. So some people get the order ABC, others get BCA, others get CAB. You use all possible orders to average out the order effects across the whole study.
Okay, last concept on the entire list. The final boss. Factorial design.
This is where things get really interesting and really realistic, because in the real world, effects rarely have just one cause. A factorial design lets you manipulate and test 2 or more factors at the same time.
So instead of just studying diet or just studying exercise, you study the effects of diet and exercise in the same experiment.
Right. And this lets you ask 3 questions. First, is there a main effect of diet? Meaning, overall, did the people who dieted lose more weight than the people who didn't, regardless of their exercise?
Second, is there a main effect of exercise? Overall, did the exercisers lose more weight than the non-exercisers, regardless of their diet?
And the third and most important question, is there an interaction effect?
The it depends effect.
That's the perfect way to put it. An interaction means the effect of one factor depends on the level of the other factor. Maybe the diet only works if you are also exercising. Or maybe exercise is super effective for people on diet A, but does nothing for people on diet B.
That's where you get the most interesting results. When you see lines crossing on a graph, that signals an interaction.
It's the key thing to look for. And just to be complete, a mixed factorial design is just a study that combines a between subjects factor and a within subjects factor. For example, comparing men versus women between on their performance before and after a treatment within.
We get it. That's the whole list. My brain feels like it just ran a marathon.
From the simplest idea of measurement to the most complex experimental designs, we covered the whole course.
I feel weirdly prepared.
Yeah.
Before we pack up our books, you had one last bigger picture thought for us.
Yeah. We started with construct validity, the idea of whether your measure actually captures the essence of the thing you care about. Well, think about life. We spend all our time measuring ourselves, right? We use grades, we use our salary, we use the number of likes on an Instagram post. Those are our operational definitions for things like success or worth.
That's true.
The provocative thought is this. Do those measures have any construct validity for a truly good life? Is a GPA a valid measure of intelligence or learning? Is a salary a valid measure of a person's value? Or are we just measuring the easy stuff, the noise, because it gives us a number?
Wow. That's a heavy thought to have right before an exam that's going to give us a number.
I know. But it's worth asking, are we measuring the right things in our own lives? Or are we just chasing scores on an invalid test?
Something to think about. Okay, well, on that philosophical note, good luck with the exam tomorrow. You've got this. We've got this.
You know the material now. Go get some sleep.
For real. Don't forget that Cozy Earth promo code, PSYC101. Your tired brain deserves it.
Boss dismissed.
This has been the Psychology Undergrad. We'll see you on the other side.